Inside most every cell in your body, you have the same 46 chromosomes carrying the same genes. But not all the cells in your body are the same. Nerve cells, blood cells, cells lining your intestine, they all look different and they do different jobs. That's because in each of these cells, different groups of genes are turned on. And when a gene is turned on, it tells the cell to construct a particular protein. Proteins are the molecules that build your body. Like collagen, a fiber that makes up much of your skin, tendons, and bones. Or keratin in your hair. Crystalline is the protein that helps make the lens of your eye clear. Some proteins do work. Actin and myosin move muscle fibers. Hemoglobin in the blood carries oxygen from the lungs to the rest of the body. So when the embryo is developing, how does a cell turn on the right set of genes and create the right proteins? Part of the answer seems to be location. Once the basic body plan is established, with the head on one end, back and front, and left and right sides, cells seem to know exactly where they are and what they are supposed to become. This is because cells talk to each other in the form of chemical messages. Chemicals in one cell can trigger a reaction in the cell next door that can spread to the cell's nucleus and turn genes on or off. But what's really going on in there? How does a gene get turned on? If all the DNA in a single cell were stretched out, it would be about 6 feet long, but it's all wound up very tightly, coiled around balls of protein. For a gene to be turned on, something has to come in and loosen up the right section. Then the cell's machinery can latch on and read the DNA, the first step on the long road to building a protein. Those molecules that can turn genes on play a key role in every aspect of development, including the process that transforms the embryo into a boy or a girl. Take a look at a 7-week-old embryo. Try to guess what sex it is. Think it's a boy? Believe it or not, this is not a penis, at least not yet. It might become one, but it could just as easily turn into a clitoris, the female sex organ. At this stage, boys and girls look exactly alike, and not just on the outside. Inside, there are 2 gonads, which could become testicles or ovaries. And there are 2 sets of tubes, one in case it's a boy, the other for a girl. Of course, there's one way to tell the difference. Look at the chromosomes in a cell from the embryo. One pair among the 23 determines sex. An embryo with 2 X chromosomes usually becomes a girl. If one of those X's is a Y, it will most likely be a boy. Recently, scientists came up with a good idea of how this works. There are only about 30 genes on the Y chromosome. One of them is called SRY. This gene seems to function just once in a lifetime, late in the 6th week of embryonic development, and only in one place, the gonad. SRY turns on for a day or 2, and the cells churn out its protein. But in that short time, SRY sets off a chemical chain reaction, turning on other genes, eventually turning the gonads into testicles, which begin to make testosterone. Testosterone travels throughout the body. If it reaches the genitals, then the cells here will build a penis. But if there are two X chromosomes and no Y, different genes get turned on and the gonads become ovaries. The embryo becomes a baby girl. This is the power of genes, creating cascades of chemical reactions, defining the form and function of all the cells in your body. Sometimes genes send the message to multiply and grow, as with the arm and leg buds. Sometimes the message is to die, as it is a few days later to the cells between the fingers. As the weeks pass, the embryo's genes send billions of individual messages, constructing new kinds of cells and building organs and limbs. Two months after fertilization, the embryo is now called a fetus. Almost all its organs are in place, though they're not working yet. The whole fetus is just over an inch long and weighs less than 1/3 of an ounce. Over the next 6.5 months, it will grow almost 400 times larger and prepare for birth. All of this demands a constant supply of nutrients. It's no surprise that Melinda might be especially hungry. The fetus she's carrying has only one source for all the raw materials it needs to grow into a baby: Melinda's blood, which is systematically raided with the help of the placenta. The placenta began to form as soon as the blastocyst burrowed into the mother's uterus, and in the early weeks it dwarfed the embryo. The underside of the placenta is covered with thousands of tiny projections called villi, which lie in pools of the mother's blood. Without ever mixing the blood of mother and child, the villi grab oxygen and nutrients. The enriched blood flows about 1.5 feet through the umbilical cord back to the fetus, whose heart beats about twice as fast as an adult's. The heart is one of the few organs that actually work during the earliest weeks of development. But with other organs, function comes later. With the eye, although the retina and lens are well formed by the 9th week, the fetus doesn't respond to light until the 5th or 6th month. And the same for the ear. The outer ear quickly takes shape, but the fetus can't hear yet. Sound conduction relies on the tiny bones of the inner ear, and most of the bones in the fetus start out as cartilage. By the 4th month, hard bone can be seen forming in the hand and the leg. Finally, after 5 months, the process is complete in the inner ear. And then the fetus begins to hear sound. Inside the womb, the first weeks are the most dramatic. Later in pregnancy, when the mother's body seems to be changing the most, life in the womb can appear, well, a bit uneventful. All the organ systems are in place, so during the last trimester, the fetus's main job is to grow. But a few crucial events are unfolding beneath the skin. Fat deposits are forming, building reserves the baby will rely on after birth. But even more importantly, fat is getting laid down in the brain. In the 6th month, genes in the brain order the manufacture of a fatty substance called myelin, which wraps around the long connections between brain cells. This fatty covering allows nerve impulses to travel up to 100 times faster, greatly enhancing brain power. The process will continue for years after the baby is born.